why is air pressure important in the atmosphere? What role does it play in the weather? Uh, Many of you may not even pay attention to the air pressure, yet it really has a major impact on what the weather will be in your area in the future. Let's take a look here in the head here. So first you got to know what it is, right? So it's a force. What is that? Well, it's mass. Mass is basically just how many molecules are in some area of air. And then there are times the acceleration. In our case, the acceleration mostly is gravity. Gravity accelerates everything down towards the ground. If you drop a rock, it falls. Uh, Newton had an apple hit his head. It started his understanding of gravity. So that is what a force is. The amount of molecules times the acceleration towards the ground. And they also give themselves a force when they hit other molecules. So the total air pressure is the cumulative force of all these collisions. And Dalton's law basically just says each gas has its own pressure, but the total pressure of the atmosphere, or the total pressure of any amount of air, is a combination of each gas's pressure. So, for example, in the atmosphere we have nitrogen, we have oxygen, we have carbon dioxide, we have water. Each one of those has a pressure associated with it. When you add all those up, that is the air pressure we're talking about. So it depends on the weight, which is basically the force of gravity. Average air pressure, 14.7 pounds per square inch. So if you think about it, your body is carrying around 14.7 pounds of pressure on it, every square inch of it. So why aren't you collapsed? That's a lot of weight. Well, everything has that same pressure going back out from air inside you. So it's totally equal. So that's why structures do not collapse. Now, if you suck the air out of something like a can or whatever, you'll just watch that can crinkle right up because of the air pressure. It's so powerful. The original measurements of air pressure were all done by mercury barometers. And they were done this way because basically mercury is one of the heavier elements, and it's still a liquid, so you can push it up in a tube. So you had a tube that had no air in it, basically. Put it into the mercury, and the mercury would be pushed up in that tube. And that's how they measured it. How high it went up is how much the air pressure was. So the average air pressure is right around 29.92 inches of mercury. Think about it. Mercury is a lot heavier than water. So if that had been water, that column would have been much, much higher. So there are other units to measure air pressure. The one that meteorologists typically use is millibars. So 1,000 millibars is basically 1 bar. And the actual inches of mercury, for example, equals 33.86 millibars. You can convert all of these. You're going to hear me talk a lot about millibars in this course, but I will guarantee you that if you listen to a local TV station, you're going to hear it in inches of mercury. Why is that? Because almost all your barometers at home and what we're used to hearing are in inches of something. They're in the English units. Millibars is a metric unit. So, interesting thing about the atmosphere, it's compressible. Well, what does that mean? Well, if you ever go in the water and try to squeeze water together, you can't. It'll just pop out. You just can't push it together. However, air you can. So that the drop in the pressure with altitude, because of that, is much greater the further lower you are in the atmosphere. The higher up you get, it's more and more gradual. Because air has weight pulling it down, so it's all compressed down towards the ground. So most of the atmosphere is in very close to the ground. The higher up you get, it's going to go slower and slower in the variation as you get away from it. This is just a variation at one station of pressure. What I really wanted you to notice is this is not a big variation. Here's 10, 11 millibars, a little bit above that, maybe 10, 12. Goes down to about 1,008 millibars and back up to maybe 10, 18, 10, 19 millibars. That is not a big pressure change. If you were to go walk up a mountain, you would discover, say you went up 5,000 feet in the atmosphere, or a little bit more, maybe 6,000. That's roughly going to be about 100 to 150 millibar pressure change. So in a mile up, the pressure is changing 10 times the amount of change you see at the surface. So there is a more significant pressure gradient in the vertical than there is in the horizontal. However, that pressure gradient in the horizontal, where it got lower here, indicates probably low pressure coming by, probably caused some rain. Higher pressure is rising. It's going to get better. Maybe some sunshine in that area. Pressure change really does relate a lot to whether the air is clear or sunny or whether it's stormy or cloudy. Another factor that weighs into air pressure is air temperature. Think about it. Air temperature means the molecules are moving faster. Now, the atmosphere is not a closed container. So what does that do? It pushes the molecules further apart if they're moving really heated. By pushing them apart, it's increasing the amount of molecules somewhere, or density is getting less. So you wind up with the air not weighing as much. So the hotter the air is, the less the air weighs. The colder the air is, the more the air is going to weigh. We're going to see that in some weather maps here today. Another influence with cold air, the molecules are tightly packed, so the pressure is going to drop very, very quickly. So let's just take a look at that a second here before we go on. So I wanted to go out of this, and we'll just look at it. Here's today's surface weather map. You see up here 1037 millibars, probably even higher than that further up. That is some pretty high air pressure. Along the east coast and down further, there's low pressure with the cold front. The low pressure up here. Again, 1033. This looks, well, here's 1,000 millibar low here. Maybe a little deeper, 998, 996 here. So the pressure gradient or the pressure change across this area is only about 40 millibars. But that is a significant pressure change. It really is causing a lot of winds, which we're going to talk about later. And as this low moves away and this high moves in, it's bringing in very cold air. Look at these temperatures up here, minus 35 up in here, minus 33. So this is a very dense air mass. And this is just starting to get into Minneapolis area, but I wanted to show you the vertical. It's at the lowest level. The cold front really is very low level at Minneapolis right now. But notice the temperatures here, minus 20 degrees Celsius, all the way up through this column right to here. And then it begins to cool down after that even more. That is a very cold air mass. So the pressure is going to drop very quickly in the vertical. And here's another look at it, and you can see temperatures here. This is a 48-hour forecast. But take temperatures out here, Minneapolis and all, and up into here. Minus 24 degrees Celsius, minus 27. There's probably minus 33 degrees Celsius, minus 36 over here. That is very, very cold Arctic air. And if you were to look at that now at 500 millibars, what do you see? Pressure dropped very quickly in the vertical, and you have 409, which is basically 4,980 meters height for the 500 millibar surface. Fairly low height, really low height, really. And that is why you can really see there's a very strong low pressure system in the upper atmosphere that corresponds very well with that extremely cold air. If this low were to come down over the United States, it would bring all that, even colder air, with it. So that's just something to think about with air pressure, how they relate the temperatures to the pressure. Increasing humidity also impacts air pressure. Guess what? Water is less dense. So just looking at that means that the more water that you have in there, the less dense the air is going to be. So in the summertime, when it feels like it's really tough to walk because it's so humid, it's actually less dense air. Kind of strange, isn't it? So another impact that makes air pressure change is converging winds or diverging winds. So if you have converging winds aloft, they're going to push the air down. If they push the air down, what's it going to hit? The ground. That downward motion is adding an acceleration to those molecules, which is helping to increase the pressure. Say the air pressure down at the ground is moving apart, which you would have to do because you can't only put so many molecules in. That's helping to keep the air pressure from going too high. But winds make a difference in air pressure. Now, ideal gas law, all it is saying is pressure and temperature are directly proportional at a fixed density. So if I know density, or if I know pressure and temperature, I know density, or vice versa. I need to know 2 out of the 3. Now, all 3 variables can change, and everything we've just talked about relates directly to this gas law. Another interesting thing with air is, as it expands, there are less and less molecules, and the temperature of the gas drops. Think about it. If you opened up your bike tire or your car tire, opened the valve, what happens when you push air out? It gets pretty cool pretty quickly. And I've been filling up my tire a lot lately, and I can tell that that's pretty much of a fact. However, if you pump air in, you're heating up that air. You're doing work to compress it. So that same principle applies in the atmosphere. So if I am lifting an air parcel up, a bunch of air upwards, and it expands, it's going to cool. That's why in the troposphere, the atmosphere cools as you go upwards. If I push an air parcel downward, it's going to warm up and it's going to get hotter. And you can see it here. Air is compressed, energy is used. That creates what we call an adiabatic process. What is an adiabatic process? There's no heat is exchanged between an air parcel. Let's define an air parcel. It is just a bunch of air. It can be 1 meter across. It can be miles across. But we're just defining a parcel of air as some quantity of air. And that air parcel then, if you lift it up, is going to cool 9.8 degrees Celsius for 1,000 meter. So 1,000 meter, a little bit over 3,000 feet. So if you were to go up 3,000 feet in height on some mountain, your temperature on a normal day would cool 9.8 degrees Celsius, a little bit over 15 degrees, almost about 16 degrees or so Fahrenheit. So if you started to walk at 70 degrees and hiked upwards, when you reach the top of the mountain, if the temperature hasn't changed in the air, it's going to be about 17 degrees cooler. So it's going to be about 53 degrees. I took a lot of classes for a while out in Boulder, Colorado. They training for the weather services out there. And we used to go up to Rocky Mountain National Park. Boulder is at 6,000 feet. Rocky Mountain National Park can go up to 13,000 feet. The amount of air temperature difference between the two places is phenomenal. It really can tell the difference in it when you're going upwards. Moisture. We're going to realize moisture actually releases heat. Remember latent heating? So if you get a moist air mass and you're releasing heat, it can't cool as quickly as a dry adiabatic air mass or dry adiabatic process would. So it only cools at about 6 degrees Celsius per 1,000 meters. So if you were walking up to a fog, you wouldn't get nearly as cold. Might feel a little damper, but it wouldn't get nearly as cold. So that's just what I really wanted to hit the points on this week. One thing I did want, again, this is an extremely cold air mass, a very tight temperature gradient here across the United States at this time in 48 hours. And guess what? Throughout this whole next week, this gradient of temperature and how it's going to evolve is going to impact your all's temperatures and mine. And later in the week, more and more of this cold air keeps coming in, so the week's going to get colder and colder, especially very up in your area and into the Minnesota area or the Dakotas. So it will be something to watch this week in the weather, and you'll be able to relate it to the pressure. Colder air, higher pressure at the surface, lower pressure aloft. So let me know if you have any questions.